I would probably suggest that of all of the topics that we've covered so far, I like the analogy of reading, learning to read. We talked about our letters, it's a periodic table. We talked about our words. That's like if I said you had AgCl, you'd all know that it's silver chloride. Last day we talked about how to make sentences. So actually, let's just do an example real quick here. Let's say that I gave you CuCl2 plus Ag. Actually, what states of matter here? Solid, solid. Could you finish the sentence? You want to take a stab at it? What would it make? Good. Cu-A... Nope, not Cu-Ag, actually. There we go, yeah. And then this is probably a solid, and that's probably a solid. Is it done, though? Fantastic, yeah. So that's kind of like the idea of writing sentences. Does that make sense, those analogies? So letters, words, sentences. This next topic, the mole, is kind of the linchpin where we actually get to now do something with chemistry. Chemistry is not just naming compounds. That's pretty boring, right? I mean, hopefully you guys are excited for, next week we're doing a lab already. I'm a huge believer that we've got to actually, here's some chemicals, let's see what they do. There's a math side to chemistry then. And so that's kind of where I was wanting to start here is the mole, I think, is one of the most important topics then because we need a way to count. We need to be able to work with numbers now. And the most common numbers that we're going to measure in a chemistry lab are going to be grams. We're going to measure how much mass something has. That being said, we have a problem in chemistry when working with mass. Okay. You guys ever heard the joke or like the riddle? What weighs more, a pound of feathers or a pound of lead?
They're the same.
And then the answer is they're both the same. You guys maybe heard that one before there? A pound is a pound. The problem is that at a chemistry level, if we're talking about particles, though, particles weigh different amounts. Like one particle of hydrogen is way less heavy than one particle of gold. Does that make sense? And so often we need to count them by particles. But that's difficult to do because particles are so small. That's why this concept of a mole was discovered. That's not the right word to use. Developed. Okay. Here's the best analogy I can give for how a mole works. You don't buy eggs or donuts usually one by one. We often buy them in dozens. Does that make sense? And so rather than saying I need 792 donuts, I say I'd rather have 15 dozen. That probably isn't exactly the same, but does that make sense? Well, that's the concept in chemistry. Rather than counting particles one at a time, we count them this many numbers of atoms at a time. That's a very odd number. You guys ever seen this number before? 6.02 times 10 to the 23? Okay, it's known as Avogadro's number, and basically it was chosen because carbon-12, if you have 12 grams of it, this is how many atoms it takes. Now, I have no idea how they counted all those atoms, but basically there's a ratio here. That means that, well, it's written right here, 1 mole is equal to a whole bunch of atoms. So rather than counting atoms in little groups, we count them in collections of groups. Okay. So let me just show you an example of how you might solve something. Let's say you have 4 moles of magnesium fluoride. I might ask you, well, how many molecules are there? I'm a big believer in trying to teach kids how to solve things using ratios. I think that works really well. So I might say something like this. Well, if there are 4 moles, Avogadro's number states that there are this many atoms in 1 mole. And so I'm kind of writing it like a fraction where there's a whole bunch of atoms in 1 mole. Would it make sense that, see how I have moles up here on the top of the fraction and on the bottom of the fraction? See how that kind of cancels? So it's kind of like me saying you have 4 dozen, but everybody hopefully knows that there are 12 donuts in 1 dozen. See how that kind of cancels? How many donuts do you have? You have 48 donuts, because that's what 4 times 12 is. Does that make sense? Well, that's what's happening here. You have 4 moles of atoms times your moles by the Avogadro's number here, and that's how many atoms you have total. Are you guys familiar with this notation here, the times 10 to the power of something notation? Is that something you guys know how that works? Okay, well, if you don't, here's what it means. If I tell you that you have 6.02 times 10 to the 23, this 10 to the 23 is a way of like shortening up a number. This is how big the number really is. 6, and then there are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. There'd be that many zeros after this number. It's an insanely large number. Rather than writing this out over and over and over again, what we've done is we've moved the decimal place over 23 times. So like here would be where the decimal place is. We've now moved it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 times. Is that something you guys are familiar with? Or should I spend more time talking about that? Okay, if you're not familiar, talk to me later, okay? So, long story short, there's a lot of atoms in 4 moles. Does that make sense? Well, a mole is a way of measuring atoms. But I just mentioned a second ago, there's a problem though, is that each type of atom weighs a different amount. And it's based on how big the atom is. For example, hydrogen typically weighs about 1. Whereas, I don't know, helium usually weighs about 4. Okay? That's where those numbers called molar mass numbers come in, like hydrogen being 1.01, and let's pick a different one. Lithium is 694. 694. These are how many grams you get in 1 mole. So it's kind of like, sometimes I use an analogy of buying donuts again. So let's say I want to go buy 3 dozen donuts. How many donuts am I buying? 36, okay? But let's say I wanted you to weigh those donuts. Does every single donut weigh the exact same amount? An apple fritter might weigh 7 grams, but a Danish might only weigh 3 grams. Does that make sense? And it's the same way on the periodic table. Although we can buy things in groups of 12, or in groups of that number, the weight of everything differs. And so that's why all of those weight numbers are on your periodic table. That's the average weight of a certain element. You guys remember when we talked about isotopes earlier in the unit? Let's say I gave you a lithium 3. What does that mean? Well, it means, maybe you could write it like this. It would be like 3 over 3. It means that lithium has to have 3 protons. How many neutrons would it have? None. It would be 0. What if I made it a 4 over 3 lithium? It still has to have 3 protons, but now it has 1 neutron. That makes sense. Or maybe there's some lithiums that weigh 5. 3 protons and 2 neutrons. And maybe even there's some lithiums that weigh 9, which would be 3 protons and 6 neutrons. Well, that number on your periodic table that says that lithium is like 6.94, the 6.94 is the average weight. So some lithiums weigh 3, some weigh 4, some weigh 5, some weigh 12, some weigh 7. This is the average weight. And so what we need a way to do then is find a way to turn individual atoms into moles, and then eventually turn that into something we can measure, which is grams. And that's what I want to show you how to do over the next few slides. So again, if you like my analogy, if I ask you to buy some individual donuts, you could buy 5 dozen donuts, but don't forget each of those donuts, although there might be 60 donuts in 5 dozen, they each weigh a different amount. We also need a way to convert using like moles to grams. So let me do some examples here. You know what? You guys can just read these slides. Let's just go right to these examples. Because I'm sure you guys remember how to do this. It's been a while. One of the things you might be asked to do then is figure out, well, how much does 1 mole of something weigh? So let's say I was giving you sodium sulfate. What is the formula for sodium sulfate? What's sodium? Okay. What's sulfate? Good. And hopefully you're getting a little more fluent at that. Is it just NaSO4, or do I need to put any 2s and 3s and stuff in it. Fantastic. Okay. So this is like you're going to the store and you want to buy sodium sulfate. But really, a sodium sulfate is made up of a whole bunch of smaller things. Sodium sulfate is made up of 2 sodiums, 1 sulfur, and 4 oxygens. So my question is, well, how heavy would I expect it to be? Does that make sense? So you can visualize this a lot of different ways. Here's how I do it. I say sodium. A single sodium donut would weigh $22.99. But I need 2 of them. A single sulfur donut weighs $32.07. By the way, do you guys know where I'm getting these numbers from? Can you find them on your own periodic tables? I have them memorized, but that's because I've been doing this for years. If you guys need to look them up, like, feel free. You need 1 of those. And then in this donut conglomeration that you're buying of sodium, sulfurs, and oxygens, you need oxygen donuts. It weighs 16, and you need 4 of them. So if you were to buy 1 mole of sodium sulfate, how much would it weigh? I got 142 of that. Okay, what does that mean? Well, that means that that's how many grams it is, and that's how many grams you get in 1 mole. Okay, here's where this gets confusing. That's more like we didn't buy just 1 donut. We actually bought like a dozen donuts. Only in chemistry, a dozen is not 12. A dozen is that like 602000000 number. Does that make sense? So if you were to have bought 6.02 times 10 to the 23 atoms, that would be considered 1 mole of this stuff. It would weigh that much. Does that relationship make sense? That's what you need to figure out. But more importantly than just figuring it out, I need you guys to know what it means. Okay? So let me try one more time in case I'm not making sense. You just bought a crap load of donuts. A lot of donuts. Only they're not donuts, they're atoms. Does that make sense? But rather than going up to the guy at Tim Hortons and saying, sell me 97,000 donuts, you actually asked for 3 dozen. Because that makes more sense to group them, right? But in chemistry terms, we don't say dozen, we say moles. So you asked for a whole bunch of donuts, but rather than asking for them individually, you asked for them in moles, like dozens. Well, then in chemistry, we want to know, though, how much do they weigh? But the trick with how much they weigh is that, well, there was actually a bunch of different types of donuts in your dozen that you bought. Some of them were sodium donuts, some of them were sulfur donuts, some were oxygen. And each of those have a different weight. So that's what this means. If you bought a whole crap load of donuts, that's how much it weighs. Does that make sense? Okay, let's try another example. I'll just erase this. Calcium hydroxide. So first I need to be able to put words into symbols. What's calcium hydroxide's formula? Perfect. With the OH being in brackets. So I ask you to go to the store and I ask you to buy 6.02 times 10 to the 23 donuts. So I'm asking you to buy a whole bunch of them. And rather than asking for that, you ask for it to be in moles. Well, the problem is that some of your donuts are calcium donuts. Calcium weighs 40.08 because calcium's a pretty heavy donut / element. When you're also buying them, you also need to get some oxygens. Oxygen weighs 16, and you're going to want 2 of them. And you also want some hydrogen donuts, and that weighs 101. And again, you need 2 of them. I got 74.1. You guys get that? Okay, throw an extra 0 on there. Convention in chemistry is that we're going to always go to 2 decimal places. And sometimes we write it like this, actually. We say that's how many grams per per, like with a line, meaning per, 1 mole. So if you were to go to the chemistry donut store and say, give me a mole of calcium hydroxide, you're actually asking for 6.02 times 10 to the 23 atoms. You're asking for a lot of them. And if you had to weigh it out, this is how much it would weigh. That make sense? Okay, one last one. Dinitrogen tetroxide. What's different about this one? Okay, so it's molecular, so a different naming scheme. Dinitrogen, 2 N's. Oxygen, 4. Tetra's 4. I don't care how you show your work for this. This is just how I do it. Nitrogen. Anybody know what nitrogen weighs? Okay, good. And you'll need 2 of those in this, I don't know, package of donuts you're buying, I guess. And oxygen is 16 right on the dot, and you need 4 of those. I got 9202. So maybe here's another way of writing that. If you went to the store and asked for this many atoms, it would weigh that many grams. Here comes the problem. When do you ever ask for this many atoms? I mean, so far we're just randomly asking for this number because I told you for that. But I mean, what happens if you only wanted 17 atoms? Or what happens if you wanted 18 more of these? Does that make sense? So this is where the rest of the math comes in, is now we need to try to find a way to kind of put this together. So, you guys ever seen this formula here? Sometimes Lav draws it like as a triangle where there's like a, I don't know how he draws it though. It's like an N and an M and an M. You guys ever done something like this before? Okay, that works. And I don't want to discourage you from doing that. But in my opinion, some of the skills we need going forward, it helps that if you can learn how to write them as ratios rather than as like different formulas here. So here's how I'm going to recommend you start trying to solve problems. Okay. Sodium hydroxide, if you actually find sodium hydroxide's like molar mass, it's 40 right on the dot. That means you could write this maybe 2 different ways. You could say in 40 grams, you have 1 mole. Or it would be valid to write it like this. In 1 mole, you'd have 40 grams. See how I kind of flipped it upside down? Mathematically, 40 over 1 is not the same thing as 1 over 40. Like, those are different numbers. But in terms of using it as a ratio to solve a problem, basically this number is like the number 1, because these things are equal to each other. 40 grams is 1 mole. So I'm going to try to show you how to solve things using ratios. So let's do an example here. How many moles would there be if we had 6 grams? So take the donut analogy if it makes sense. You go to the donut store and you say, sir, I would like to buy 6 grams worth of donuts. So I don't know, you guys ever go to Marble Slab? Or what's the other ice cream place in Lethbridge where like you pay by the weight? You guys know those places where like you fill up the bowl and they weigh it? Yeah, that's the one, right? Where they charge you by weight. So imagine that you went to a donut store, and at the donut store you said, I want to only buy 6 grams worth of donuts. Right. Then the question you have to ask then is, well, how many donuts should you be given? Does that make sense? And so, well, the first question you have to ask is, well, how much do they weigh? Am I buying apple fritters, which are really heavy, maybe? Or am I buying Boston creams, which are light? So, how heavy is sodium hydroxide? Well, we just did it a slide ago, but let's do it again. Sodium hydroxide is 2299. Oxygen weighs 16. And hydrogen weighs 101. And that just happens to work out to like 40 right on the dot. So a little bit of mental math. If I wanted to buy a full dozen / mole of donuts, it would weigh 40 grams. I only want 6 grams. So am I buying a full mole's worth of donuts? I'm buying considerably less than a mole. That makes sense? If I wanted a full dozen worth of donuts, it would cost me 40 grams. But I only want 6 grams. So am I buying a full dozen? No, I'm buying like a partial dozen. So here's how I'm going to recommend you set this up then. I would say you have 6 grams, and then the ratio can be written one of 2 ways. So I'm going to show you 2 different ways of writing it. You could say that in 1 mole there are 40 grams. Or you could flip it the other way, and you could say in 40 grams there is 1 mole. Which one of these 2 ways of solving the problem is correct? Anybody know? It's the top one. Here's why. See how this gram symbol right here cancels with this gram symbol right here? Because one's on the top and one's on the bottom. This is solving things using like ratios. Whereas look at this bottom one right here, which is not going to be the right way of solving it. See how this gram symbol right here and the other gram symbol, they're both on like the top? That doesn't work. Also, 6 times 40 is like 240. But didn't we just say that like this was going to be way less than a mole? Okay. So what's 6 divided by 40? 0.15. Oops, that didn't come up very nicely. 0.15.
Can the following students please come to the office at the bell? Diane Davis, Larissa Blackrabbit, Lexi Wells, Celine Rogers, and Trez Daychief. Please return to the office.
No, I would just say now moles. The gram symbol that was right here has canceled with the other gram symbol on the bottom. So what this means is you went to the store and you asked them at the store for 6 grams worth of donuts. Right? And they weighed them up, and the first thing they discovered is that the donuts that you bought were 40 grams per 1 mole. So then how many moles do you need? Let's change the word moles to dozen, because maybe that makes more sense. You wanted 6 grams, and it costs 40 grams per dozen. How many dozen do you need? Well, you don't even need a dozen. You need way less than a dozen. So they're going to give you like 0.15 of a dozen. Only in chemistry we don't use dozen, we use moles. Is this something familiar that you guys have done before? I really want to recommend ratios. They're so useful in solving chemistry problems. I want to just give you maybe like an everyday life example. Let's say that you went to work for 10 hours. How much do you guys get paid per hour? How much? $10 an hour? Okay, so let's say that you then made $10 per hour. Do you see how like the hours symbol cancels? How much money did you make total then? $100. Would you write it like this though? You went to work for 10 hours, and in 1 hour you earn $10. Would you basically take 10 and times by 1 and then divide by 10? Like, is it 10 times 1, 10? And then divide by 10, be back to 1? That means that you earned $1. That totally doesn't fit, does it? But if I read it like this, then you could say, oh look, 10 times 10 is 100, and the unit that's left over, I made $100. Does that make sense? I can extrapolate this to all sorts of crazy scenarios, and when we will, I might say that, I don't know, let's take this again. You worked for 10 hours, and you worked for, let's see, every 1 hour, you earned $15. And then let's say that you want to buy something, and you want to go buy eggs. And so eggs cost $3.25 for 1 dozen eggs. And then you could say you're then going to use those dozen eggs to throw at someone's house. I don't know. And so it takes, let's see, there are 12 eggs. No, I got to do this the other way around. In 1 dozen, there are 12 eggs. And then you could say that at each house, oh my goodness, I'm running out of room here. That's the word house right there. At each house, you throw 3 eggs. I could go crazy and say, well, actually I screwed this one up. I did, didn't I? Hours should be on the bottom here. Shoot, I totally messed it up. Let me try that again. Okay.
Leland Bastine, can you please come to the office? Leland Bastine, please come to
10
the
hours.
office.
So let's say you worked for $15 an hour. See how those cancel? And then you could say that, let's see, 1 dozen eggs costs $3.25. So now how like the money symbol then cancels? And then you could say that there are 12 eggs in a dozen. So that cancels there. And then you could say that you're going to throw 3 eggs at every house. This is kind of ridiculous. What I've now calculated is a way to figure out if I go to work for 10 hours, how many houses I can egg. Very indirectly, like it took a long ways here, but what you do is you'd go 10 times 15 divided by 325 times by 12 divided by 3, and that would tell you how many houses you could egg. So 10 times 15 divided by 3.5 times by 12 divided by 3, you could get to 171.4 houses, apparently. Okay, does it make sense though? At least the point I want to make is the idea of how you can like cancel out things using ratios.
Leland Bastine, please come to the office for a phone call. Leland Bastine, please come to the office for a phone call.
If you guys can follow the how I've canceled things here, that's a useful skill going forward. Okay, let me finish off with the last couple examples and I'll be done for the day. Back to my donuts example. You want to go to the store and you want to buy a quarter, basically, 0.24 of a dozen donuts. My question is, how heavy would it be? So, do we know how heavy sodium hydroxide still is? 40? So I might recommend write it like this, 0.240 moles. And what I want to do is I want to multiply it by a ratio. For my ratio to work, I want this mole symbol right here to be able to cancel with something. So that means I want to put moles on the bottom here so those can cancel. And I want to put grams on top. Perfect. So the 40 grams goes on top. If you wanted to, you could put a 1 on the bottom. What this means is that in 1 mole, it is 40 grams. So then multiply. 0.240 times by 40. I got 9.6. One of the reasons why I like showing this then is what unit goes behind this number? Grams. And the reason I know that is because it's the only unit I didn't cancel. That make sense? Usually for 2-step calculations, it's not bad. But this last couple of examples, I want to do like a 3-step calculation, which is what we're going to do on part C here. Okay, take it from the top again. You go to the store and you want to buy 2.5 dozen water donuts. How heavy will they be? Well, the first question you have to ask is, well, how heavy is water? So what's water's formula? H2O. So hydrogen is 101, you need 2 of them, and oxygen is 16. So I got 2802. No, that's a different one. 1802. 2802 is like methane or something. So here's how I might recommend writing it then. You want to buy 2.5 dozen moles. I'm going to put moles on the bottom then, so that they can cancel, and put grams on the top. Where does the 1802 go then? On the top, yeah. So 2.5 times 18.02, 4505. What units do I use then? How do I know that it's grams? It's the only unit that's left. Let's go backwards then. What if we started with 1120 grams of water? Would it be right to use 18.02 like this and just times by 18.02? I'm going to say that's not going to work. Because look, here you have grams on the top, but look what's on the bottom of the fraction. Good. Yeah, you flip your fraction upside down. Here we're going to put grams right here. And I'm going to say that we need 1 mole to go on top. And I need 18.02 grams to go on the bottom. You see how those grams can now cancel?
So then would you divide?
Yes. If you need to, what you could do in your calculator is to type 11.20. You could times by 1 if you wanted to. But timesing by 1 is kind of pointless, right? So then, like you said, then you're dividing. So 1120 divided by 18.02. Okay, do you guys know what sig digs are? So sig digs are basically letting you know how much precision we have in our measurements. This went to 4 significant digits. This one here also went to 4 significant digits. So I have the answer of 0.621533161, like that. So this has 4 digits, this has 4 digits. This guy right here has to have 4 digits as well. Do you guys know the rule, though, that zeros in front don't count for significant digits? Okay, good. So then 1, 2, 3, 4, that's where we're going to stop. 0.6215 moles. If I need to go over sig dig rules, let me know. I can do that later with you if you want. Does that make sense? Okay, one last example. If you like the idea of how these ratios cancel, it can be useful if you've got multiple steps. Rarely am I going to give you questions where you just do one step. Like, we're getting to more complex questions. So here's what I'm asking is, how many water molecules would there be in 1120 grams of water? Here's how you might solve this. In 1120 grams of water, we can convert that into moles using the exact same ratio I just did, 1 mole over 18.02 grams. But I'm not done yet. I don't want moles. I'd like to know how many molecules there's going to be. How many donuts are in a dozen? 12. How many molecules are in a mole? Exactly, it's that 6.02 number that we haven't actually used yet, but here's how we would use it. I would then say, well, in 1 mole, there are 6.02 times 10 to the 23 molecules. So this kind of says, go to the store, I want to buy 11.20 grams worth of donuts. This says, well, here's how heavy a dozen donuts are. And this says, this is how many donuts are in a dozen donuts. And so I might recommend we can do this all in one big step. I can have this grams cancel with this grams. This moles cancels with this moles. What's the only unit I have left now? Molecules. That's what I wanted. It said how many water molecules are there. So mathematically in a calculator, you need to do 1120. You have to divide by 18.02. And then you have to times by that Avogadro's number. And so here's what I got. You would then be buying 3.74 times 10 to the 23 individual donuts, or in this case, molecules.
So that's one like, so you have the 3.74, and then here it has like an E and then 23, that means that would be 10 to the power of 23.
Yeah, if your calculator does an E23, that's times 10 to the power of 23.
Okay.
Why don't I do one last example before we take a break here? Because that was my last slide, correct? Okay, so let me do one last example, maybe 2 more. Just want to make sure you guys have this. If you had 3.12 times 10 to the 50 atoms of gold, how much would it weigh? So here's a typical quiz question. I'm going to give you a whole bunch of atoms of gold. How much do they weigh? So first place I might start then. Oops, didn't mean to do that. Let's write out 3.12 times 10 to the 50 atoms. I don't really want to work with atoms anymore. So I'm going to put atoms on the bottom of my fraction so that it can cancel. Does that make sense? The problem is I need to have some sort of ratio that I know that involves atoms and something else. Anybody know a ratio that involves atoms and something else? Like, say, moles? That's the one we just used. There are 6.02 times 10 to the 23 atoms in 1 mole. Yeah, see how like atoms could then cancel? What units do I have left right now? I don't want moles though. I wanted weight. What is weight measured in? Okay, so I need another fraction before I keep going here. I need to get rid of moles. See how moles will then cancel? And I need to put grams on top. Herein lies a really big question then. How heavy is gold? $196.97 in 1 mole. See if this makes sense. We started with a whole bunch of atoms. And I've canceled my atoms like this. That told me how many moles I have. But moles is just like how many dozen I need. I don't care about how many dozen I need. I want to know how heavy they are total. So then this moles right here canceled with that moles right here to find me a weight. So the thing you need to do then is take this number and divide by that number, and then times by 196.97. And that'll give you your weight. It's probably going to be insanely high. I picked a really stupid number to start with. Yeah, it's probably really large. This many atoms, 10 to the 50 atoms, is probably ridiculous. It's probably way too big. Why don't I make this 10 to the 23 instead of 50? Because that was kind of ridiculous. Make that a 23 for exponent. You guys able to get 102.08? Okay, let me show you how that would look in your calculator. I would go 3.12 times 10 to the power of 23. And then I'm going to divide. When you divide, I'd recommend you put that whole thing in brackets though. So like I'd make it 6.02 times 10 to the power of 23. Put that whole bottom part of the fraction in brackets, because otherwise what your calculator thinks to do is it divides by 6.02, but then it times is by 10 to the 23. We want to divide by the whole number. And then lastly times by 196.97. I'm guessing you didn't get 102.08 then?
I got 102.
Okay. And then did you get an E afterwards though? Okay, so that's why it's not working out correctly. Because what your calculator is doing is it's taking 3.12 times 10 to the power of 23, and it's dividing by just 6.02. Then it's timesing by 10 to the power of 23. So it's almost like this 10 to the power of 23 is on the top of the fraction. We don't want it to be on the top of the fraction. And then that's timesing by 196.97. And so you guys are probably getting this number here, which is way too high, because that's not how many grams gold is going to weigh. Devin.
I'm getting 0.51.
Is that just when you did this one divided by this number here? Because you haven't times by the 196.97 yet. That's why. Should I do one more example before we take a break? Okay. I can do more if we need to. How many atoms would 1.5 grams of methane contain? Let's try this one. How many atoms would 1.5 grams of methane contain? Probably. Okay, so here's how I'd recommend you start. Start with the 1.5 grams. Can I convert 1.5 grams to something else using a ratio? Yeah, let's use molar mass. See how I can get rid of this grams and this grams right here? Yeah, put a mole on top. Next question though, how do I find that molar mass? How do I know how heavy methane donuts are? I guess first question, what is methane? Good, okay, so methane is CH4. So that would be carbon is 1201 and hydrogen is 101, but you need 4 of them. So this one is, I think, 1605. So if you were to have 1 mole of methane, it would weigh 1605. Do we even have a mole of methane then, if we only have 1.5 grams? So we have 1.5 grams. A full mole would require 16 grams. Do we even have a mole? No, we have very, very little of a mole. So I might write it like this then. In 1 mole, there's 16.05 grams. And now my grams have canceled. But I don't want to know how many moles of something, because that's like dozen. I want to know how many individual atoms there will be. So that's Avogadro's number again. So I could then say, well, in 1 mole, see how the moles cancels right here? There are 6.02 times 10 to the 23 atoms.
How would I put that in my calculator times the brackets?
I would definitely recommend that anything goes on the bottom of a fraction. Probably brackets on the bottom makes sense, but especially with scientific notation. So take 1.5, divide by 16.05, and then times by 6.02 times 10 to the power of 23. I got this. 5.6 times 10 to the 22. That's how many atoms you would have in 1.5 grams of methane.
Yeah, let's start off.
Good. Do you guys want to do one more, or do you think you have the hang of it? I would, yeah.
It's so dumb.
Do you guys feel comfortable?
Yeah.
Okay. Okay, why don't we call it there? So basically going forward here, that should have been in 5 lessons and basically just under 2 weeks. That should have been all of Science 10. It's kind of crazy to think that would have taken you 2 months last year. We just covered it in like under 2 weeks. So my goal now is, let's write my unit test on it and see where you're at. Okay. I think you need to get pretty proficient at this though. Okay. One thing I'm noticing even when I'm asking you guys some questions, it's taking you still quite a while to know what compounds are. Like if I said NH4NO3, ammonium nitrate. I need you guys to be quite proficient at that, because chemistry is not just about naming or about being able to recognize words. We have to actually do something with this later. And so if you don't know your words fluently, so that you can just look at it and say, I know what that is, you're not at that place where I need you to be yet. Does that make sense? So that might be something you want to work on over the next day and a half. Sound good? Okay, last thought. If you want practice on this mole stuff, on my website, if you were to go to the notes section here, the 5th review booklet here has stuff on the mole, the pictures of Avogadro's number. But basically it's a whole bunch of questions where you can practice molar masses and then practice converting moles to grams and grams to moles. So if you want that practice, feel free to print it off. If not, I don't care. Sound good? So the rest of today, all of tomorrow, is kind of free time to study. So ask me questions if there's something you don't know, and then Wednesday we're writing a test. So go take a break if you guys need.